Right, I'll start on London's explanation for superfluid. Now, London's explanation is to think of the helium atoms, the helium-4 atoms in a superfluid. Alright, so there are lots of helium-4 atoms in there. It's to think of this as particles of bosons in a gas. So in other words, it's a very big assumption. It assumes that these particles behave like in an ideal gas where they don't interact. Okay, so for now let's suspend our disbelief and see where this leads us. Now, the reason why, a main reason why London or how London justify this assumption is the results of the heat capacity that he obtained making this assumption. Well, with the assumption that the helium liquid is like bosons in an ideal gas, he obtained the result that the heat capacity of this system, this boson gas, heat capacity and temperature, it looks like this, below about 3.1 Kelvin. It comes down to 0 with a curve, and above 3.1 Kelvin it comes down as well and tends to the value for the ideal gas. Alright, if let's say this is the heat capacity per mole, then this would be 3/2R. So I'll talk about how this is obtained afterwards, but for now the justification eventually for making this assumption is that this calculated heat capacity actually looks like the measured heat capacity. So this is the calculated one. The measured one looks like this. There is a peak at about 2.2 Kelvin. There is a much sharper peak, and then it comes down again after that. So that's our lambda point, or lambda curve, because it looks like lambda. So it looks similar, alright, even though there's some difference in the temperature and the shape, as well as in the nature of the transition, which we shan't go into. And the other idea about the boson, using a boson gas, is the idea that at very low temperature, the particles of bosons, they all go into the ground states. We imagine the energy levels. So nearly all of the particles will go in the ground state with very few on top. So since all or nearly all the particles go to the ground state, they will all have the same wave function. Alright, and we know from the Broglie's relation, momentum is equal to h over lambda, that for very low energy or even zero energy, momentum will be zero, so the wavelength will go to infinity. Alright, or if it's not exactly zero, the wavelength will still be very large. So this means that the particles here will have a very long wavelength. Wavelength that can be as big as the bucket holding the liquid. So, and they all will have the same very long wavelength. So together, all of the particles of helium might even act like a single wave function. So there is this idea that we have the same giant wave function. Alright, the terms that have been used are giant or macroscopic. Right. It's like the whole bucket of helium is a single giant wave function. So that's something really strange. And it turns out that it's actually it has actually been shown that it does demonstrate many of the properties that you would expect with this idea. So that's the background, or rather the overall idea. But what we are going to do is to look into some of the details of how this heat capacity is calculated, and what are some of the predictions and perhaps measurement results that eventually justifies this picture to some extent. Right, so now if you recall from what we've done previously with particles like ideal gas, electrons, phonons, and so on, we have a general method for finding the heat capacity, right? And the strategy is usually that to find the heat capacity, we need the total energy. Okay, because from the total energy we can do du dt to find the heat capacity. Alright. And to find the heat capacity, we can do that if we know the density of states, number of particles per state. Then we can integrate this, multiplying by the energy, and in principle we can find U. Okay. And in order to find this, we need to know density of states and that and F. So we need these two things that go into there. And for the density of states, we have found in all the last few cases we've studied that we can actually take it from the ideal gas density of states. Simply because that's the assumption that we started with, and in the hope that it will give us the correct answer for the heat capacity. Now, so likewise we would make use of the ideal gas density of states for a start, and then we would have to make some changes depending on the system. Like for electrons, we have to multiply by 2 for the 2 spin states, bosons, phonons by 3 for the 3 polarizations. Now, but in the case of bosons, real bosons, not as in virtual ones like phonons, we don't have to, because the bosons are real particles, so we can simply take over the ideal gas density of states and use it here. We don't have to multiply by anything. And the F E, so that's the number of particles in one state at energy E. Well, if we think of it as if we think of it as a set of all the possible values at different energies, then this is really a distribution over energy. And you remember how we got that? We got that using the Lagrange multiplier method. And if you remember what we did before, we had to consider the most likely macro states, the number of ways we can arrange particles among the energy levels. So this we have not done before. We've done it for electrons, phonons, and ideal gas. Now all of this has slightly different conditions. Okay, ideal gas assumes that there are many more particles than many more states than particles. So for typical, well, for any of the energy intervals, and that leads to certain simplifications. And for electrons, we need to make use of the exclusion principle, which says that no more than one electron can occupy the same spin states. So, but for bosons, it would be, for real bosons, it would be different from all those, and we have not done it before. So let's start on this. Now, before that, let me just write down what we do know about the heat, the density of states, just to make sure that we've got everything. So the density of states formula for the ideal gas, let me write it to one side here. That is GE is given by, let's see if I can remember it, 4 pi m V for volume divided by h cubed, and then square root of 2 m E. Okay, I hope that's correct, but please check your notes. So let's start on the Lagrange method to derive this. Now the method is the same as for the ideal gas. Imagine lots of energy levels, and we'll consider one interval, the E. Alright, and suppose that this is sent around or centered at the energy EI. So I have another interval, lots of intervals above and below it. So that would be interval number I minus 1, that would be interval number I plus 1. So that's interval number I. And the energy at the center is EI, just a small interval. And we look at the particles. Imagine that there are some particles distributed around here. Okay, and we want to find the number of arrangements in here. Now, just before this gets too abstract, let me remind ourselves as to where we are heading. Now we are heading towards this Lagrange function, which is the log of the number of arrangements of the particles plus terms involving the constraints. Number particles must be fixed, total energy must be fixed, and we introduce the additional unknowns lambda 1 and lambda 2 which are called Lagrange multipliers. Then that's the function that we need to maximize if we want to maximize the number of arrangements, in this case with respect to let's see, what are we doing with respect to? With respect to n1, n2 and so on, that would be the number of particles in each interval, subject to the constraints that n and u are constants. Okay, so the way to do it is to maximize L. So what we are doing now is the same as what we've done for electrons and ideal gas. We want to find an expression for that in terms of these. So let's start from the interval number I. The number of ways we can arrange the particles in interval number I, let me call that omega I, and we need some terms. Let's see. That particle, let's say the number of particles here in the interval I, let's say there are ni particles and there are the Gi states represented by the line, and we want to know how many ways are there of arranging these two things within that interval. Now if you remember, for the electrons, in order for the exclusion principle to hold, I've assumed that the ball would be stuck to the rod, right, as I thought of the particle and the states. So I'm going to think about, again, the particle as little balls and the lines as little rods. Now this time there's no exclusion principle, so that means no restrictions at all. We are free to arrange them any way we like along this column. So we have this number of particles which are identical, this number of states. Let's think about it as ni balls and Gi rods. So how many ways can we arrange these two number of identical particles? Well, the total number would be ni plus Gi. So if they're all different, it would be this number factorial. But because ni are the same, we divide by ni identical particles. And because the Gi rods are the same, divide by Gi. So that's it. That's the way to do it. So eventually, we'll need to make omega from here. And the way to make omega from here is to say, right, this is number of arrangements within one interval. Now to get the number of arrangements, omega, over all intervals, for all energies of all particles, we need to multiply the number of arrangements for all intervals. Okay. And eventually, if I take the log, this would be log omega 1 plus log omega 2 and so on. Alright, now since we want to maximize L, the Lagrange function, that means we eventually have to differentiate this. And if we differentiate this, well, we would be differentiating with respect to each of the n1, n2, and so on, the number of particles in each of this level. So if I'm differentiating with, say, by ni, for example, alright, for a particular ni, I'll find that these terms here, this one, you see that omega I depends only on ni. So omega 1 depends only on n1, omega 2 on n2, and so on. That depends on ni. So that if we differentiate this with respect to ni, all of these terms will be 0 except for that one. Okay. So this is really just di by dni. And that simplifies things. Now, let's look back at this omega I formula. Now we need to differentiate log omega I. Now let me take a log of that. Now remember that we need the Stirling's approximation. Let me take the log first. So log of omega I is equal to log of ni plus gi factorial minus those log of ni factorial minus log of gi factorial. Okay, so that's what I need to differentiate. Now, and we need Stirling's approximation for this. Now, if you remember, Stirling's approximation looks like this. N log of n factorial is equal to n log n minus n. So that's Stirling's approximation, which we need to use. So let's put this in. So this would look like ni plus gi log ni plus gi minus ni plus gi. Okay, that's what it looks like. That one would be minus of, put a bracket around it, ni log ni minus ni. That one, gi log gi minus gi. Okay, now we are ready to differentiate by ni. So let's let's notice that that term does not depend on ni at all. So that becomes 0 when we differentiate. Now let's deal with this. When I differentiate, I'll have, let's see, that's a product. So I'll start with differentiating that. That's a constant, so that differentiates by ni to 1. So that's just 1 times log ni plus gi plus, and then I need to differentiate this. So this is ni plus gi. I'm using the product rule here. Times derivative of that would be 1 over ni plus gi. So you see that they cancel to give a 1. And then minus, to differentiate that which gives 1. So 1 minus 1 is 0, so those two cancel. Right, I'm just left with that. And likewise, when we carry this through, alright, we'll find differentiate that, get log ni, plus differentiate, differentiate that, get log ni, differentiate that, you get ni times 1 over ni, differentiate that, you get 1. So that cancels, and you're left with that, and that's differentiates to 0. Okay, that wasn't so bad. Let's simplify. So I have this. Those are gone. And then I have that. Those are gone. Now we are ready now to go back to the Lagrange function. We are ready to differentiate that. Now it helps if you remind yourself what we'll get when we differentiate n and u. Okay, so let me write down that as well. Perhaps on this side. Now n, if you recall, is n1 plus n2 and so on. Now u is n1 e1 plus n2 e2, so on. So now, if we want to differentiate the Lagrange function, remember what we need to do? We need to differentiate each of these separately. So that, we already have the answer. That's this one. Alright, that's the answer. So we can write that down now, actually. So if I differentiate dl by d and I, I will get this. Okay. Now then, when I differentiate n, now this is n here. If I differentiate by ni, all these will be 0 except that one which will differentiate to 1. So I have plus 1 times the Lagrange multiplier. Likewise, when I differentiate u, okay, all these will be 0 except the term with ni. Ni differentiates to 1. I'm left with ei, with its Lagrange multiplier. So we have differentiated L. Now what remains is to say that at the maximum this should be 0 and we can solve for ni. So let's simplify this. I'm going to try and combine those two. Now what we want is to solve for ni. Okay, so if I combine this, ni plus gi over ni, that's those two. Now I'm going to try moving those to the other side. So I get minus lambda 1 minus lambda 2 ei. And I'm going to invert the log. That gives e to the minus lambda 1 minus lambda 2 ei. And now I'm going to try to make ni the subject. So, okay, so ni plus gi is equal to ni e to the minus lambda 1 minus lambda 2 EI. Okay, then GI, bring that over. And then I can factor out Ni and make it the subject. So we're almost there. Okay, so I'm going to do it up here. So Ni is equal to GI over those. GI over E minus lambda 1 minus lambda 2 EI, right, minus 1. So we have found Ni. Alright, well, not exactly yet, but because we still have the lambda 1, lambda 2, which are unknowns to think about. Now, but we know how to deal with those. Minus lambda 2, right, oh, okay. I said lambda 2, we know from earlier results that for electrons, or for the Boltzmann distribution, that lambda 2 is minus 1 over kBT. Right, and lambda, that's lambda 2, and lambda 1 is a constant which we can solve in terms of the total number of particles in principle. Alright, lambda 1 is determined by the number of particles, and like for the case of electrons, which has a very similar form for its distribution, we are going to use mu for the lambda 1. We are going to take lambda 1 to be, just let lambda 1 be mu over kBT, where mu is another constant. So we are just going to express this unknown in terms of another unknown called mu, which is called the chemical potential. Okay, so this means that we can now write this expression in terms of those two. So let's do that. Start on a fresh piece of paper. Right. So that expression there in terms of this now look like Ni is equal to Gi is that times, I'm going to write this as 1 over this lot, which is exponential of, okay, that EI minus mu, have a bracket over it, factor out the 1 over kBT, and minus 1 from there. So this is the expression, and then we are going to do what we did for electrons. We are going to say, right, since the EI, remember where the EI came from, refers to that particular bundle of energy levels. Okay, and we needed I because we divided them into intervals, and I was used as a counting number to count the intervals like 1, 2, 3, 4 and so on. But we can now drop the interval I and just refer to the energy by its own value. Right, so that means that I can now write this as, I can now replace EI by just E. Now the other thing that I would also do is I would divide both sides of this equation by dE. And I would do that because I know that the number of states in the interval divided by that interval is the density of states, which we know. Okay, and number of particles there divided by dE is also the familiar number density per unit energy that we have seen for electrons and ideal gas. So now we drop the subscript I and call this just E minus mu over kb T minus 1. So now we have our distribution. Okay, and this lot here corresponds to the function Fe that we have seen before, which represents the average, which is physically the average number of particles in one state at energy E. Okay, is that all the occupancy number? And this formula, okay, is called the Bose Einstein. Oh, I should use capital letters for respect. The Bose Einstein distribution. So we've just derived the Bose Einstein distribution. Okay. Now let's remind ourselves what we started off doing. We wanted to, let's go back here, we wanted to find the heat capacity, and we know that we can do it if we know the total energy. So really, this is what we're after. Okay, so let's write down what we have and see what we can do with it to get our heat capacity. Coming back here. Now, so the U here, let's see what it looked like in its full glory. Oh, okay. We know what it looks like. It's E, G, E, F, E, D, E. So this is just the number of particles in the interval dE times E. Now GE, okay, I put an E here, and we know what GE is. It's from the ideal gas, 4 pi m big V over H cubed times square root of 2m E, and oh right, and that's GE, and then we have FE, which is this, which we now know. So it's 1 over this long expression again, and then dE. Now that doesn't look easy to integrate. We should not forget the limits of 0 to infinity. Okay, unlike phonons, which has upper limit, bosons are real particles, so energy can be as high as there is energy available. Right. So putting aside the difficult that this equation might be difficult to integrate for the moment. Let's look at whether we know enough to integrate. Now, m would be the mass of the helium atom, v the volume, h the Planck's constant, kb temperature. All this we would know, or we could find out, or if not, we could always assume some typical values. Now, but that one we don't know, the mu, the chemical potential. So it's the same problem we had, which we have seen for electrons and for the Boltzmann distribution. There is that unknown that we need to solve for. And we know that it can be related to the number of particles. So before we can even do anything with this expression, we need to deal with the chemical potential. Okay. So let's look at how it relates to the total number of particles. Now the total number of particles, n, would be, coming from there, you can get that simply by integrating GE FE, just adding up all the particles in each interval. It goes from 0 to infinity. So this integral would look pretty much the same as this, except that it doesn't have an e. Right? E is absent here. So you can imagine writing this whole lot out. Now that in itself is not very helpful either, because like before, it's a difficult integral to integrate, and it would be very difficult to find mu. So instead of trying to deal with this complex expression, what we could do is to look at Fe. Look at this Bose Einstein distribution, and think about it physically. Think about what it means physically, and see if it can give us some idea that might help us to simplify the calculation. Okay, so let me therefore write down Fe. Fe equals to 1 over P minus I. Okay, now let's take a break and I'll come back in the next video clip.